Hi everyone, this is biomes. So I'm going to do a video since I'm out today, but I want Blue Day to have this lecture. So here we go. So we're going to talk about biomes today, and we will start with climate versus weather. So what is the difference? And politicians mess this up all the time. Weather is the short-term state of the atmosphere. The snowstorm we just had, a rainstorm, what is happening on the scale of hours or days. Climate is the long-term pattern of the weather, where we can only observe the weather. We can't observe the climate per se. So we look at the weather and patterns in the weather over long periods of time, and that tells us what the climate is. And the climate is what determines the biome. All right, so that's a great video. If you want to go into the slideshow and watch it, I highly recommend that. All right, so why are biomes the way they are? Because of temperature and precipitation. And here's a map of the main biomes of the world. There's some variation on these depending on who you're asking, but these are the basics that you're probably already familiar with, sort of the tundra, ice sheets, polar deserts, all the way down through the forests and into tropical rainforests. So today we're going to talk about how do biomes get to be the way they are and where they are. So what controls temperature and precipitation of the biomes? And the answer is differential heating of the atmosphere and the oceans. How does that happen? That's what we're going to talk about today. How do we get differential heating of the atmosphere and the oceans on Earth? Well, let's look at it. All right, I'm going to talk about three main situations here, three main that go into what controls the temperature and the precipitation, or how we have differential heating. Number one, insolation and the latitude. We're going to talk about how the sun shining on the Earth gets us to the tropics being very productive, high solar radiation, consistent day length, versus the poles that are on the opposite end of that spectrum. We're also going to talk about atmospheric circulation. We're talking about global atmospheric currents. In today's lecture, we're going to talk particularly about Hadley cells. There's a lot of different ones, but we're going to concentrate on that because it is very determinative of biomes, where warm air rises at the equator, cooler air sinks. And that forms the deserts. So I'm going to show you how that works. And then we're going to talk about how those biomes end up banded along kind of latitudinal lines, how that heat distribution shows us those, it results in those bands. All right, so let's start with the first one, insolation and latitude. And the point I want to make here is that the sun is shining on the Earth. Now, remember, the Earth, this is what gives us the seasons. The Earth is tilted at 23.5 degrees. And that tilt is important, but certainly for the seasons on Earth. And the sunlight is shining here on that equator. And what I want you to notice is that sunlight is shining at a very high angle, like 90 degrees, okay, to the surface of the Earth. That is very direct sunlight. Lots of energy being transferred to the Earth from the sun at the equators. So remember, that's where our tropical rainforests are. Why do we get so much productivity? Because there's so much sunlight, insolation entering the system, giving us lots of energy to kick off those ecosystems and those producer layers. Now, if we go up to the poles, we have the opposite situation. Look at the angle of the light. That makes a huge difference. We have a low angle of light. A lot less energy is able to be entered into the ecosystems at the poles. Therefore, what do we have? Ice, low productivity. All right. So one thing I do want to point out, because it's a common misconception, is some people think, well, when you look at this picture, you think, well, maybe it's colder at the poles because they're that much farther away from the sun. Like that's a pretty big distance, right? Well, the answer is no. That is an insignificant distance between the sunlight hitting here versus the sunlight hitting at the poles up here. It really is the angle of the sun, this high angle, versus this low angle and how much energy penetrates the atmosphere there. So it is not the distance that it's further away from the sun here. It is really the angle of the sun. All right, so that's great. We have this, have different amounts of sunlight energy or insolation entering the atmosphere from the equator to the poles. That's differential heating of the atmosphere. How are we getting to biomes? Well, let's look at the second point, atmospheric circulation. Because we have that differential heating, we're heating the atmosphere differently. That leads to global winds. Did you ever notice in America, like up here, all right, here we are, this is Europe, but we're over here, that all of our weather comes from the west? Well, that's because we live in the global wind pattern known as the westerlies. And notice there's one in the northern hemisphere, there's same in the southern hemisphere. They have a westerlies zone as well. Now, next to that, between the westerlies and the equator, we have the trade winds. Trade winds, think of like colonization. Ships are coming across this way. They get into those trade winds and help them get across. That's how those ships went. So, same thing in the southern hemisphere as well, because those winds travel from the east to the west. Polar, we're back up, actually has an west flowing from the east as well. Polar easterlies. Okay, so, because they alternate. We end up with these cells over here. Now, they're a little bit hard to understand how that works, so I'm going to show you in the next slide. But where we're headed is that at the equator, we end up with hot air. We have a lot of insolation, right? A lot of sun coming in here. We heat that air. It rises. Hot air can hold more water, and so it rises up. Then it translates over here and down to there, and it cools once it's up in the higher atmosphere, and then it cools and cooler air sinks. It's more dense. It's also drier. It can't hold as much water. So it sinks down at about that 30 degree north and 30 degrees south. So let me show you what this looks like in a better picture. Here's what it looks like. This is called a Hadley cell. So you notice we have the tropics, right? We have that warm air heated. It's wet because warm air can hold more water than cool air. We know that, right? Because in the summer, it's humid. In the winter, it's very dry. That's why, because warm air can hold more water vapor than cold air can. So that warm air rises lots as it hits the cooler air aloft. It rains out. We have tons and tons of rain in the tropics, lots of productivity there in all those plants. That air cools off, it moves to the north and to the south, and then now it's drier, it's cooler, and it descends down. And notice what we get at those 30 degree north and 30 degree south latitudes, we get deserts. Okay, so that's why we're going to see when we look at our biomes, we tend to get deserts on our planet at 30 north and at 30 south, and we get tropical rainforests at the equator. So this is a huge reason why we have the biomes where we have them. And what is I'm going to remind you, what caused this ultimately? Differential heating of the atmosphere from the sun, the angle of the sun. That's what caused this. All right, and here we go. Here's that pattern. And if we just look at a sort of satellite imagery here of the Earth, you notice we know we have rainforests across here. Here's the Amazon in South America, Central Africa, lots of tropical rainforests, and of course Malaysia, Indonesia over here, some of the most famous tropical rainforests on Earth. Along the 30 degree north parallel, the desert I grew up in, the Sonoran Desert over here in the southwestern US and Mexico, the Sahara Desert, the most famous desert, across Saudi Arabia, and across Asia, Gobi Desert, and then down here we have the Atacama, South America, South Africa down here, and Australia. So those deserts tend to be at 30 degrees north and 30 degrees south. Why? Because of the Hadley cells. And here we end up with the basics of our banded biomes. We have tropical rainforests, across in a band around the equator. We have those dry climates because of those Hadley cells and that somewhat cooler, drier air dropping down and sinking because it's more dense at the 30-degree north and 30-degree south parallel. Then in between, we have temperate climates with seasons, and this is where we are. Here we are, right there. And then above that, the polar climates where we have that very low angle of insolation coming in. And here's the biomes. So let's take a look here at a map of the actual biomes. And we notice, of course, at 30 degrees, we have our deserts. We looked at the satellite picture just a second ago. This is just a drawing of those. We have the deserts across here at 30 degrees south, and we have these green tropical rainforests across the equator, generally speaking. Now, this is not the only thing that plays into biomes and where they are. There are other factors, and two that I want to point out to you. One is elevation, which is also going to play a role. As we go higher up, we, of course, lose temperature, about 3 degrees per 1,000 feet or so. And we also have ocean currents that are playing a role in here. So let's talk about those. All right, so it's not just latitude that makes a difference. Elevation also plays a role. So we do have, if you start, my favorite place to look at this myself is, of course, in Hawaii, Mauna Kea, Mauna Loa, on the Big Island of Hawaii. If you ever have a chance to go, because you can sit on the beach and be in your bathing suit, be happy with a fruity drink in your hand, maybe, and you can drive in about 2 hours. You can drive to the top of Mauna Kea, Mauna Loa. There's an observatory up there, and you will need a parka because it's so cold, because you've just gone up roughly 14,000 feet in 2 hours, and you are going to travel through different biomes as a result of that. So that is another, but this is true all over the world. It's just nice to see it in Hawaii, where you can go from one extreme to the other in a very short distance. So you can always think about elevation is also playing a role in terms of what biomes are present. All right, and now ocean currents. Ocean currents are really important too. So the basis of, just like we have global wind patterns, we also have global ocean currents. And if you actually dropped a packet of water that you could, a parcel, for example, up here in the North Sea, we often think of this as the beginning up here of the conveyor belt, just for no reason, just because. It actually is, that parcel of water will travel the entire planet. It will go all over and end up back where it started. So it really truly is a conveyor belt. And it probably take like on the order of like thousands of years to do that, to make that trajectory. So, but something I want to point out to you, for example, that you're probably, like, if you think about it, you're aware of. Notice how on the eastern shore of the United States, here's the United States, that water, that Gulf Stream that's coming up is coming from the equator. It's coming from warm waters, all right? And it's carrying warm waters. Well, there's a lot of exchange between the oceans and the atmosphere. So the temperature of the oceans drives the weather for sure, okay? It drives hurricanes, it drives our storm that we just had. Like, it's a really important aspect of the weather, and then therefore long-term the climate. So if you think about why is Florida so warm, oh my gosh, it's this Gulf Stream, you know? It's not just the latitude and the insolation, how much sun there is at what angle. If you go across to California, this is a different situation. Look, the water coming down the coast of California is actually coming from the polar waters. It's much, much colder water. And that is one of the reasons why California has such moderate climate. So in the summer over here, we're getting warm, humid summers, 90, 95 degrees. California, they're staying at 75 degrees over there on that coast. Part of that is because they have that cool current coming down. We have a warm current. Another aspect of this I want you to notice is this warm water comes across and goes all the way over to Europe. Europe has very mild weather, climate, relative to its latitude. And so where we have over here at this given latitude a temperate climate, they have the same temperate climate, even though their latitude is farther north. You'd expect it to be much colder. So that is because of this warm Gulf Stream coming from the equatorial waters. It's warm, and it carries that warmness over to Europe. So let's take a little bit closer look at that. See this arrow right here. Notice how these biomes don't line up exactly across latitude. Everything's shifted north here because of that warm Gulf Stream coming across. So I just want you to notice that. So we're back to why are biomes the way they are? We've just gone through several reasons. Temperature and precipitation. And that's all related to all those dynamics we just talked about. All right, so how do we see that? Well, climographs are a great way to see that. And climographs are just a real nice way to look at an area, a biome, a microbiome. And this is a way to look at the location over time, and they always have like January to December. That's the months, the first letter of each month. And then they'll have a precipitation, usually on the right, but it can be either way. You'll have a scale for precipitation, and that's usually the bar graphs are precipitation, average precipitation per month, and then on this side, the temperature, degrees Celsius, and that's the line graph, generally speaking, for climographs. And it's like, okay, so in the summer, it's hot, in the winter, it's cold, so on and so forth. So you can look at those different patterns, and then keep in mind, of course, that the southern hemisphere has our winter is their summer, and reversed. So you can look at the different patterns here to see what the climograph is. And each biome is going to have a different climograph pattern. And I'm going to invite you to watch this video in your slide deck, and it explains it really, really well and goes through the different biomes and what the pattern is. All right, the next thing I want to show you, net primary productivity. So we have our net primary productivity. Remember, that is our gross primary productivity minus the energy it takes for respiration of the producer layer. So why does a tropical rainforest have a massive NPP while tundra has very little? So let's look at this. We have all of our biomes here, and their productivity over here, their NPP. And notice we have over here tropical rainforests, estuaries at the far right, very, very productive, lots of plants, deserts, tundra over here, low net primary productivity. And so you can think about those, and then forests, generally grasslands in the middle. So you can think about, okay, all of those things we just talked about, how much rain there is, how much insulation is coming in, that differential heating of the atmosphere and the oceans, and how does that play into net primary productivity? And there definitely is a correlation there. So, all right. Now, the Earth, as it looks right now, is not always how it has looked. So here is a picture of the Earth 250 to 300 million years ago. We call, due to plate tectonics, all of our continents were actually, they're always moving around, kind of like puzzle pieces, floating, moving around through around the Earth, and we think it always looks like it does now just because that's when we're alive, but it looks different all the time, like it's constantly changing on geologic time scales, obviously not on human time scales. So you can see here we have South America, we have Africa, North America, Europe, Siberia, China, India, Antarctica, Australia. Those at one time have all come together into one giant continent. So that kind of changes things a bit, but does it? So we have this enormous ocean, the Panthalasic Ocean out there, Tethys in here, but we have this giant continent. So let's think about biomes 250 to 300 million years ago on Earth. And here is a picture of that. So it's a little bit hard to see, but here's our Pangea, right? Here's all our continents outlined in the black, all those islands that you saw back here. All right, so that's what this looks like. And here's our biomes put in there. Now remember, the biomes are primarily determined by that differential heating of the atmosphere and the oceans from the insolation. So that hasn't changed. The continents can move around, but that insolation on the Earth has not changed. That angle, it doesn't show it right here, but the angle of the Earth, that hasn't changed either. 23.5. That's from long, long ago, probably from when a very large body hit the Earth, forming the moon, is probably when we kind of got knocked off our axis in terms of our tilt. So we have this Pangea, and we put the biomes over it. And notice we have that same pattern, right? We have at the 0 degrees, we have our tropical, summer wet. Yes, lots of heating, hot air can hold more water, therefore we're going to still have those Hadley cells set up between 0 and 30 to the north and 0 and 30 to the south. Warm air's rising, lots of rain happening there, and we get those tropical rainforests. Now, that air moves across, it goes higher up in the atmosphere, it cools off, it dries out because the rain falls out of it. We now have dry, dense air, it sinks down, and what do we see on the 30th north parallel here, or latitude? We have deserts along those 30th north. So even 300 million years ago on Earth, we still see basically the same patterns of biomes on a large scale. 30 south, we also see deserts. 0, like up here, or 90 degrees rather, in the poles. 0 is the equator. 90 at the poles, we see cold, temperate, or tundra type biomes. On more localized scales, I can tell you the ocean currents are going to be totally different than they are now. Those ocean currents are very much driven by the where the continents are. So that's going to look quite different. But that basic heating, differential heating between the equator and the poles is going to basically look the same no matter where the continents are. So our basic large-scale biomes are going to look about the same throughout Earth history. All right, so biomes, we've been talking about the largest scale of the biomes, but they really are kind of almost fractal, right? Like where you can have microbiomes depending on those latitude, or, latitude kind of determines the major biome characteristics, but elevation can change things. Those ocean currents can have changes at a smaller scale. So you can look at this Southern Africa, whereas this might be kind of 1 or 2 biomes on the largest scale. Now people can separate it out into a myriad of different sort of smaller scale biomes. So I just want you to be aware that that's happening. We can even go to a smaller scale. Off the coast of Africa, Madagascar. Here we have Madagascar. Even on that single island, it's not one biome. At the micro scale, we do have these microbiomes. And I talked to you about Europe earlier, how everything is kind of shifted to the north because of those ocean currents coming across the Atlantic Ocean to warm things up and kind of shift those biomes to the north, the colder weather ones to the north. But anyway, Europe has specific ones. So I just want to show you that biomes can be kind of much smaller scale than the huge ones we look at on the whole Earth scale. Like this. So this is when we're talking about the largest scale, we kind of separate them into about 9 or so, 9 or 10. And this is sort of what the pattern looks like. All right, another thing I want to just point out briefly is something called the PE ratio, the precipitation and evapotranspiration rate. And this is pretty straightforward. If I could just move myself over there. So if you notice, we look at the annual precipitation, annual P, in some unit of measurement. They're using millimeters in this table. And then the annual evapotranspiration from the plants, the producer layer, also in the same unit, and for a rainforest versus a desert. So notice that the precipitation in the rainforest, very high, 2,500. In a desert, very low, not a lot of rain, for that Hadley cell reason we looked at. Annual evapotranspiration, relatively low in the rainforest. The air is already humid. In the desert, quite high. Okay, so now when we take the PE ratio, we take the precipitation, we divide it by the evapotranspiration, and in the case of the rainforest, we're taking a high number, 2,500, dividing it by a low number, 1,200. That gives us a number greater than 1. That is a high PE ratio. So that's going to have high productivity, high PE ratio. That tells us something about the biome. In the opposite sense, the desert, we have a low annual precipitation divided by a high evapotranspiration. We get a number lower than 1, and that gives us information about that biome. So you can do this you make this calculation for any of the biomes and kind of figure out where you are between these two extremes. All right, and then I wanted you guys to kind of look at this. I want you to kind of look at this chart and spend some time with it. This will definitely be like on the test, and look at the patterns that you notice. So just make a note, notice 3 patterns that you notice from this table of data. Let me point out just a couple. This is looking at the net primary productivity, the annual precipitation per year for those main biomes. We're looking at the area over the earth, the plant biomass, the mean biomass, and the animal biomass. Notice our 10 to the 6th here, 10 to the 6th here. Be careful what you're looking at. Plant biomass, 10 to the 9th. So this is a much bigger number than this number, okay? So this is 3 orders of magnitude bigger than this. So watch your units there. And then the solar radiation that you would see generally in those, along those latitudes where these biomes are found. So kind of look through here. Some things I'll point out is your plant biomass is quite high for tropical rainforest. We kind of know that, right? We've learned about that. And also our annual precipitation, very, very high. Where you have a lot of rain, you have a lot of producers. Okay, that's one thing I might notice. Let's go the opposite, desert. All right, so here we have a whole lot of area. That's the highest area covered of the terrestrial biomes on Earth. Our plant biomass, the lowest, and our precipitation also among the lowest. Okay, so not a lot of precipitation, not a lot of plant biomass, not a lot of producers. So there's lots of things to kind of look over in this when you look at the slides, and you can compare and kind of think about the meaning and how we get from how we create biomes, right? Think about what I said to begin with. What makes a biome a biome? Temperature and precipitation. Temperature and precipitation are going to lead you to net primary productivity, plant biomass, animal biomass, all right? But you're going to start with solar radiation, temperature, precipitation. All right, and so here is your project. So I want you guys to kind of to work only pairs or singles, no groups of 3 in this project, okay? So figure out who you want to work with, or if you want to work by your own, that's fine. And you're going to go ahead through this project. You're going to make a slide deck, 6 to 7 slides. Here's the outline of them. You have a title and a location. For your biome, there's a specific sign up you can do. I have lots of specific biomes listed if you're having trouble figuring one out, and you can go in and sign up for one. And then I want you to do a slide on the abiotic profile, describe the geology and the topography. Consider including a climograph for your specific location. That would be great. 3rd slide, the biotic realm. Identify the dominant producers and consumers and include one specific food chain that's unique to this location, to this microbiome that you're looking at. The productivity analysis, research the net primary productivity for this biome. Maybe look at the PE ratio. Is it high? Is it low? Explain specifically how the climate limits or promotes growth of that producer layer here. Talk about those animals and those plants that live there. What are they limited by, if anything? Number 5, the conservation status. This class always kind of circles back on itself, and so we're going to revisit those conservation topics that we studied earlier in biodiversity. I want you to identify one endangered species of some kind or another, and maybe the primary threat to them: climate change, deforestation, desertification, eutrophication. Like, what is happening in your biome to that endangered species? Then I want you to compare it. Look in the textbook, and you'll notice there are summaries of each major biome type on page 181 to 187. And how does your specific location, your kind of more microbiome, how does it differ from the textbook description of that biome? And then I want you to cite your sources, as including your images. Go ahead and put those in the last one. And you are welcome. I don't want you using AI to write the rest of this.